Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to lecture 34 of this course on machine learning for Earth System Science. Today we are beginning module 5 where we will be discussing the applications of machine learning for Earth system modeling. The topic of this lecture is just to introduce you to Earth system modeling and give an idea of how machine learning can help. So we will discuss various concepts of Earth system modeling and we will see their applications also, and finally we will also discuss this concept of physics informed machine learning. So like this is just like today we will not discuss any research papers, we will just like see or understand the different concepts of Earth system modeling. So first of all, what is Earth system modeling? So in different stages of this course we have been making references to different process based models. We have talked about numerical weather prediction of NWP or using weather research and forecast. We have talked about global climate models, regional climate models and so on. So like we have also mentioned that there are these process based models for different kinds of Earth system processes, like for climate, hydrology and all these things. So what do these models do? They basically simulate the Earth system processes, and most of these models are based on differential equations. That is to say, there is a set of equations which we call as the governing equations of the models. So like there are of course the variables corresponding to the actual meteorological variables and so on. And so what most of these process based models do is that they define certain differential equations over these variables. Say for example, there are some of them are say toy models, like Lorentz 96. Lorentz 96 is a toy model which considers two variables. You can say a fast moving variable like whose value changes rapidly, and a slow moving variable whose value changes slowly, but they are coupled. That is, the slow moving variable has an impact on the fast moving variable and vice versa. So like basically like the time derivatives of both variables are mentioned using two differential equations. So those two are the governing equations of the Lorentz 96 system. So that is of course a toy model, as I said, but the actual models for the different processes, they also have governing equations which express the time derivatives or whatever of the different variables in terms of that is each other and so on. And so most of these model equations, they are based on some laws of physics. Say for example, conservation of mass, conservation of balance energy and so on. And now whenever we want to do any kind of simulation by these models, the initial conditions are provided from which the simulation starts. Then thus this simulation proceeds by solving the differential equations at regular time intervals. So like the US Energy Department has brought out this like this cartoon. So it shows different sets or we can say different families of Earth system models. So these for the atmosphere we have the global water model, extreme water model, extreme weather model, clouds and convection model, aerosol models and so on. Similarly, there for land we have the soil hydrology models or vegetation dynamics models, plant process models, human interaction models. Yes, for ocean also we have ocean current and eddy model, this salinity model, sea ice model. Similarly for the cryosphere, for the ice based models are like the glacier models, ice sheet models, etc. So like each of these themselves can be called as Earth system models in their own right, but an integrated Earth system model will have all these into will take all of these into account. Say for example, this MIROC is ESL ES2L. So like that is this MIROC is basically the name of an agency which has brought out this model. So this is supposed to be like an integrated Earth system model. It was initially developed as a climate model only, so like which includes the atmospheric physics, the ocean physics and the land physics, and but the Earth system model retains this climate model, but also adds some other components like the ocean biogeochemistry, the land biogeochemistry and so on. It also so this model, this Earth system model, this also receives the various extraneous variables. So if you remember in like our earlier lectures where we are discussing how to develop statistical models using latent variables and so on, we mentioned covariates or extraneous variables. So like lots of these variables are intraneous to intrinsic to the model, that is the model actually specifies equations for for how those variables may behave, but then there are certain other variables or covariates which are not explicitly modeled, so they are provided as inputs, like external inputs to the model. These include the solar emissions, the carbon dioxide emissions, greenhouse gases, etc. So these are either they come from outside the Earth system, as in case of solar, or they come from human dynamics, which are not of course modeled in this or taken care of in this model. Now, what is the aim of Earth system modeling? What do we hope to get out of it? So first of all, we want to understand the interactions between the different components of the Earth system. So like as you can see, so like here like there are so many different components, and as you can see, these arrows, these indicate the interactions between the different components. These MAD0 or COCO as is written here, these are actually sub process models. So for oceanic physics there is this COCO model, for land physics there is this MAD0 model. So these arrows indicate that some outputs of these models are being provided as inputs to the ocean models, and similarly here there is a bidirectional input output relation between the ocean model and the aerosol model, that is the aerosol impacts the ocean and the ocean also impacts the aerosol, and so on and so forth. So these kinds of interactions, these we can form a better idea of these interactions between the different components using such models. Then arguably the most main reason why these models are so important now is for understanding the future scenarios. So say for example climate change, that is these models might be these general circulation models, the GCMs, as developed by various various research groups under the IPCC, the Intergovernmental Panel for Climate Change. So these models are run for several years or several decades into the future, and they give us some idea about how the world's climate might be in 2050 or 2080 or something like that. Now of course that depends on certain extraneous variables, like they say how much carbon will be emitted by the human beings depending on the result of the amount of industrialization we achieve or urbanization we achieve, or whatever technologies we adopt and so on. So those are the extraneous variables to the model, but what it does is under different scenarios related to emissions, these models try to give us an idea about what the future climate may look like. And also that is of course very far into the future, but what about something very specific or a specific event, how a particular event may pan out. Let's say for example a flood or a cyclone or an earthquake. Say suppose a cyclone originates somewhere in the Bay of Bengal or at this particular location in the Bay of Bengal, then in what ways it can move, which all regions it can affect, at what speed it may make the landfall, and how much damage it can cause. So these kinds of what is the specific, or how much time does it can it possibly take to make a landfall. So also we can understand how a specific critical event like that may pan out, so that we can have some idea about how to plan for such an emergency. then we can also estimate the impact of possible interventions. So suppose like we decide to scale down on industrialization, or suppose we start using more of solar technology by eliminating the use of fossil fuels. How does that alter the climate change scenario? So or even for a very more localized process, if I make some kind of interventions, so like for example, like here also, as you can see, these extraneous variables. So suppose I artificially change some of these extraneous variables, how does the result change as a result of that? And finally, visualizing various counterfactual scenarios. So counterfactual scenario means something that has like is a hypothetical scenario which has not happened and which we have no idea, no way of knowing. Say for example, now we every year we see several cyclonic storms happening in the Bay of Bengal, which strike the eastern coast of India. Several like 2-3 of them are happening every year. Earlier also they used to happen, but it seems the frequency has increased, their intensity may also have increased. Now some people say that this is happening as a result of climate change. Some other people may say that there is no climate change, otherwise also it would have happened. So like then the question is, had climate change not happened, that is like say suppose we had still been stuck with the climate as it was say 150 or 200 years earlier, then also could we have expected this kind of an event, that there are being an increase of frequency of cyclones and so on? Could we have expected such a thing? So there is no prima facie, there is no answer to this question, because the climate has changed. It is not what it was say 150 or 200 years ago. It is then how can we possibly say what would have happened if the climate change had not happened? So these kinds of what if analysis, they can be achieved with the help of these models. It is possible to initialize the model to the pre-industrial period, say around 1840 and so on, and then without any further carbon forcing, just allowed the model to run till this time, and then we could see if actually there are certain periods where these cyclones over Bay of Bengal had become more frequent or not. Now this process of developing Earth system models, this is fraught with challenges. So challenges are manifold. So first of all, as I said, these models have governing equations which are which indicate how the different variables interact with each other. The problem is that first of all, many variables are unknown, that is we do not even know which all variables are maybe crucial or maybe useful for these processes, and even if we know, like we may not be able to measure them. So there may be certain variables, say we know that there is wind speed 500 or 5 kilometers above the earth's surface and so on, but such variables are difficult to measure. So like unless we have measurements, there is no way to validate the model or to parameterize the model and so on. Then secondly, the relations between the different variables are also often not known. Also the governing equations of the models which we are talking about, so these are based on certain physics based laws, but those laws have been devised by scientists based on empirical observations. Those laws may not necessarily be perfectly true, or they may be only approximately true, but certain other factors may have to be brought into it. Say for example, Newton's laws of gravitation, or like say for example, if I release a ball from a high point and allow it to fall to the earth's surface. Now Newton's laws of course tell me how long it will take to hit the earth's surface and so on, but in addition there are many other effects like say air resistance, viscosity and so on, which are not taken care of by Newton's laws of motion. So those are like additional corrections which we may have to make. So similarly in these governing equations also, like it might be necessary to make various other corrections bringing more effects and so on, which we may not know as of now. Then finally these models or the governing equations, they have various parameters, coefficients and so on, whose actual values we may not know. Now these so first of all, those good things may be entirely hypothetical, and secondly, like their values may change from location to location, from time to time, etc. Now these usually what happens is that some experts specify the values of these parameters based on again some empirical observations, but as I said, the variations of such values and so on are usually like not taken care of in these models, and they result in certain biases. Then another very important thing is that every model has a particular resolution. So we have been discussing right from the beginning about spatiotemporal modeling. So that is any model, be they these process models which we are talking about now versus or the statistical models which we had talked about in the early lectures, each of them will need a particular spatiotemporal structure to work, a grid system to work with. So there will be certain spatial resolution, temporal resolution and so on. Now whatever resolution we are working at, let us say the 50 kilometer by 50 kilometer or something like that, or like hourly or daily in temporal dimension. Now there may be subgrid processes which we can also call as unresolved processes, that is some process which is limited to say only 20 kilometers or say like which occurs over only a few seconds or a few minutes and so on. So such processes are like they are not taken care, they are too small for the model to take care of. So we call these as unresolved processes. So in the models we just like consider these subgrid processes as a source of error, or at most maybe some kind of parameter or coefficient, right? The problem is that like the various but these processes are neither like a coefficient or nor is they some random noise. There is actually a process behind it, only we are not able to take it into account. So as a result of this, some bias is often added in these models, and which and these bias keeps getting accumulated, as a result of which, as the process runs for the simulation runs for a long time, the output keeps further deviating further and further from reality. And most another very crucial factor is that the high resolution models like they are very expensive to run. That is one way to circumvent the problem of subgrid processes is to of course reduce the grid size and make the model as high resolution as possible, so that there are lesser and lesser unresolved processes, but that also makes the model much more computationally challenging. And a typical climate model today requires like an elaborate supercomputing system to run, and then also it runs for like a very long time, and in the process it consumes a lot of electricity and emits carbon and so on, and it may itself this process itself may be contributing to climate change. And so so in general this is a very big limitation of these kinds of models. Also now okay, so suppose we have the theoretical basis of a model somehow developed in spite of all these problems, then also first how do we calibrate the model and how do we evaluate the simulations? So like one way to do it is with the help of data assimilation. So like the model will start with certain initial conditions which we may have specified, and then we will allow it to run, but like as the model is running, we will keep providing it with observations. That is the model will be estimating the values of different variables, but we will be from time to time providing the actual values or observed values of those variables, so that the model can calibrate itself and tune all its parameters at each step. So this is basically the data assimilation process, for which we have already studied one approach, the Kalman filters. So apart from so Kalman filter is only one way. There may be various other approaches to data assimilations which these models can be making use of. Then if we are evaluating say short term simulations, then we can compare the final output of each variable with the observations. But if we are doing a long term simulation, then its evaluation, it's kind of pointless to that is do a pointwise comparison of the different variable values. That is to say, let us say I am simulating the Indian climate for say 50 years or 100 years or something like that. In that case, it will not make much sense to that is every year see if the models that is simulated values match the corresponding years observations and so on, because like if we are running it for such a long period, then making a point to point measurement is like we cannot expect it to be accurate point by point. So instead what we can do is like we can measure the various statistical properties. Let us say we focus on one particular region, let us say Kharagpur, and see whether the mean temperature of Kharagpur as simulated by the model over this period, like is it does it resemble the actual mean temperature of Kharagpur for the same model as observed in reality, or what about the variation, what about the maximum and minimum values, and so on and so forth. So this way, like we do a statistical comparison of the simulated variables versus the observed variables. Now so this is all about earth system modeling, but where does machine learning come in here, or in other words, what can machine learning do as to help this process of earth system modeling? So there are many things it can do. First of all, knowledge discovery. As already mentioned, there are various governing equations used for these models, and these are based on our the laws of physics that we know, but then there may be some additional relations or additional laws, additional equations which we do not know. So it is actually possible to use machine learning to find new equations. In fact, there is a paradigm of equation discovery which is used in physics informed neural networks, which we may briefly touch upon in one of the subsequent lectures in this module. Then most importantly, uncertainty quantification. That is, most of the process models are deterministic, but we know that there is a whenever we are making any kind of forecast or any kind of simulation into the future, we can never say anything in in concrete terms. There will always have to be a notion of uncertainty. That is, instead of making a pointwise prediction, we should always be able to give some kind of a range or confidence interval. Now most of the deterministic climate or earth system models are unable to do that. So to achieve some kind of or to quantify the uncertainty of these processes, one way to do it is by using machine learning, especially the probabilistic models. Next, better data assimilation and calibration for the parameter estimation. So machine learning already provides an elaborate framework for parameter estimation. So some of the, as I said earlier, most of the parameters of the earth system process models, they are just expert suggested values, which may have flaws. They may be varying over space, varying over time, and so on, which is which no expert can specify beforehand. But using data and also using the different frameworks for parameter estimation, which is known to the machine learning community, it might be possible to estimate these parameters in a much more robust way. And then we can have a better representation of the subgrid processes which we just mentioned. So instead of just specifying it as a random noise or some kind of parameter or coefficient, the machine learning, we can instead have a machine learning model for those subgrid processes. That is, the variable the earth system model can work in tandem with machine learning algorithms, which which you can say are like proxies for those subgrid processes. That is, they do not actually simulate those subgrid processes, but given a certain condition, the machine learning model can actually predict what those subgrid processes will cause, and then those causes of those subgrid processes, I'm sorry, the effects of those subgrid processes can be then plugged into the earth system model for further simulations. So so this is one very important way in which machine learning can replace the can help in the better representation of the subgrid processes, which is a proverbial Achilles heels for the earth system models. Then causal analysis we have already talked about, that is like an earth system model is not very useful unless it can actually preserve all the causal relations. One reason for this is, we have mentioned, one of the most important applications of earth system model is in understanding how the system may react to some kind of intervention. That is, if I manually reduce the carbon dioxide content in the atmosphere by some kind of manual intervention, then what will happen to the system? So, like for that, so this is a question of causality. Carbon dioxide is the cause, but what are the different effects? Like unless the earth system model that we are using is able to preserve these causal relations, then it is not very useful. That is, then it will not be able to answer the question which I just asked in a very accurate way. So, it is necessary that any earth system model should be able to preserve all the causal relations that are actually observed in the from real observations. So, this is like we have already discussed the concept of causality and how machine learning can be used for causal inference and so on. So, this is another way in which machine learning can help. Then finally, when these earth system models are run for a very long time, so they will generate a huge volume of data. Now, from that, how can we extract useful information? Say, suppose I want to understand say how many droughts will be taking place in such and such scenario of climate change, or how many rainfall anomaly events will take place. So, for that we need various machine learning algorithms, because we cannot expect to sit and manually analyze those vast volumes of simulation data. Then I may also be interested in certain variables which are not directly modeled by the which are not directly simulated by the model, but I may but they may be related to the variables which are actually simulated. So, in that case, that relation between the simulated variable and the target variable, that may be represented by a machine learning framework, and then so based on the various future scenarios or various simulated scenarios, I may be able to know the possible values of the target variable that I am interested in, even though the process model the earth system model itself does not give me that. Then apart from that, we have already discussed explainable and interpretable machine learning techniques, those layer wise relevance propagation and backward optimization and things like that. So, suppose a model makes a prediction, the idea is to understand why it made such a prediction, that is, which part of the input caused it to make such a prediction. So, suppose an earth system model actually gives me some wrong result, that is, I simulate it for a particular duration, and starting from an initial condition, and I find that what it gives me as output does not match what is actually observed. So, then I want to understand what went wrong, which components of it gave wrong results. So, so then one way to do it is to use some of these explainable AI techniques to see which parts of the input or the initial conditions are actually important for determining the output, and that will give me some idea about what is wrong with the model. Is it that it is not taking certain parts of the input into consideration, or is it putting extra emphasis on some other parts, and so on and so forth. Then one very important way in which machine learning can help is in developing surrogate models. So, what are these surrogate models? So, we have already discussed that these the process earth system models, they require very high computation power and time. So, now instead of running those huge models, can we actually use some low cost machine learning models which does not aim to simulate the entire earth system, but maybe focuses only on certain parts of the earth system, and like it will so for any art system model, it will be able to, the machine learning model will be able to tell me what that art system model will simulate for any given input for a particular variable. So like so it in a sense it is like learning the behavior of the model. Given any particular input, it should be my machine learning model will be able to tell what the process model is going to give me. So this helps in speeded simulations also. Now how is this achieved? One way in which this kind like machine learning can be used for all these things in art system models is with the help of physics based machine learning. That is, the machine learning will not like, of course, the all the machine learning algorithms that we are familiar with, the neural networks, the random forest, the Bayesian networks, Markov random fields, etc., they will all be there, but they will have to be tweaked in such a way that they are suitable for this purpose. That is, they are consistent with the physics of the system. So the process models are all based on the laws of physics, but the machine learning models as such are not based on that. That is, it is possible to for a machine learning model to make such a prediction which will not obey any law of physics. Say for example, conservation of mass may be violated or something like that. So one way to achieve that is is first of all through the model variables. So like some of the model variables of the machine learning model, they can correspond to the process variables. So like if you remember the statistical models which we discussed in our early lectures, so some of those the latent variables, they are supposed to actually represent the latent and observed variables. Some of them are supposed to represent actual physical variables, and the natures of those variables, the typical range of values taken by the variables, etc., can be incorporated into the model variables also through things like, say, conditional probability distribution, etc. Then we can have like a very important way is to use the physics guided loss functions, which in a sense measure the deviation of the prediction by the model with the laws of physics. So let us say the machine learning model produces input y corresponding to produces output y corresponding to input x. So but it turns out that the output y is inconsistent with the physics. That is, let us say conservation of mass is violated. In that case, we can design a loss function which shows by how much the mass has been the mass before and the mass after, what is the difference between them. So ideally, of course, it has to be 0, but it will take some non-zero values. So that non-zero value will be recorded as the loss function. And then we know when we are training the model model parameters are optimized so as to minimize the loss function. So it will try to tune itself, calibrate itself in such a way that these physics based laws will be nearly equal to 0. That is, the outputs will have to follow that particular law of physics. So if there is such a model which whose output must follow multiple laws of physics, so for each of them we can have a separate loss function, and all these loss functions can be added together so that all of them must simultaneously be minimized. And then additionally, it can also happen that the architecture of the neural network, or for the architecture of the Bayesian network, or whatever we are talking about, that itself encodes the various laws of physics in some way or the other. So this is this is a famous paper which appeared in 2019, which discussed how deep learning and process understanding for data driven art system science. So here so let us say this is a sub model of an art system model, and it has its own input as well as its own parameters, and it has outputs and so on. And then there are these observations and ground truth levels, etc. So now according to this cartoon, the machine learning model can be used as an interface between the ground truth and the model output. That is, the machine learning, what the machine learning model will do is it will compare the model's outputs with the ground truth and send feedback to the model that you need to calibrate yourself to bring down the loss and so on. and the machine learning alternatively the machine learning model can itself like indicate or be like used to say estimate the various values of the model parameters for which the model's output will estimate the ground truth and so on. So these are the different or a few relevant papers related to how some of them give examples of ART system models, and some of them give some idea about how machine learning can help in these ART system models. Even 3-4 years earlier, the art scientists were not particularly keen on this matter, but nowadays for the last few years a realization has been coming to the art system scientists that machine learning can actually can not only help but perhaps even like take over the way they have been doing the art system models, and that's why we are hearing of terms like neural art system models, where the model equations will no longer be based on say differential equations as they had been earlier, but by machine learning models or neural networks or Bayesian or graphical models themselves. So in the coming lectures, the last few lectures of this course, we will see certain applications of these art system models for various specific applications. So till then, bye.